Welcome back, folks. I know this has been a lot to throw at you. It's a little different than the things we've been doing. So I want to look at two examples that I think will help you kind of piece together how all of these things are related. I want to start with a time domain plot that you might get by using an oscilloscope to measure one of these signals. I want to take that plot, figure out the time domain mathematical expression that represents that signal, and then from that find the phasor. Then in the next video we're going to do it backwards, and I think that's going to help you relate all of this stuff. What do we see in real life when we put it on the oscilloscope? How do we represent it mathematically in the time domain? And how do we represent it mathematically using a complex number in what we call the phasor domain? So I'm hoping this helps to kind of piece this all together before we start doing circuit analysis on it. How are we going to measure it, and then how are we going to use it in circuit analysis? We got to connect those two things. So here's an example for you, and it's a waveform. I generated it in MATLAB, so I have the answers hidden. I haven't looked at them. Why would I cheat? You think I would cheat? Never. Anyhow, so here's our signal. And if we want to find the time domain function first and the phasor second, then we're going to have to figure out the pieces of information that define the sinusoid. And there's three pieces of information that we need to measure off of this plot in order to write the time domain function. The first one we're going to start out with is amplitude. Okay, and amplitude can be expressed in a handful of different ways. We've really only talked about one, and I didn't make it explicit, but we can talk about amplitude as a peak voltage. We can talk about amplitude as a peak-to-peak voltage. And then one that we're not going to cover in this video, but I want to include it here just so that I'm complete, is something called the RMS voltage, also known as the effective voltage. We'll cover that in a future video, why that one's important. But peak voltage and peak-to-peak voltage we're going to talk about here, and that's because this is used in the time domain. Squeezing it in here, and phasor forms. Okay, so why not read that right off the plot? Well, the reality is that the peak-to-peak voltage is easier to read off the plot. Okay, so we can relate those two. It's as simple as some of you probably suspect it is. Okay, so I'm going to find the peak-to-peak voltage, and then I'm going to convert it to the peak voltage, because that's what I'm going to include in my time domain function and my phasor domain function. So let's do that. So let's see here. Can I do it out here? I'm going to do it out here. Okay, now let's do it with yellow. The peak-to-peak value is exactly what it sounds like. Find the positive peak, okay, and figure out what that value is. So to my eye, it looks like it's halfway between 2 and 4 on the scale. So we're going to call this positive 3 volts. Okay, finding the negative peak down here looks like it's about halfway between -2 and -4. So let's call that -3 volts. And the peak-to-peak voltage is simply the distance between those two. Okay, so if I'm 3 volts above ground on one peak, 3 volts below ground on another peak, then I'm going to have a total of 6. Let's figure that out down here, and we'll say the peak-to-peak voltage, and you'll see it drawn this way sometimes where it's V sub peak-to-peak. You'll even see that in the unit. We can say that it is 3 volts minus a -3 volts. So I'm taking the positive peak and I'm subtracting the negative peak, and that's going to give me 6 volts peak-to-peak. We include that double P down there when we want to be absolutely explicit about what voltage we're measuring. Okay, if we want to take that and convert it to just the peak voltage, it's really quite simple. Divided by 2. Okay, out of a 6 volts above, 6 volts below, halfway is 3 volts. Okay, so we take that 6 volt peak to peak, we divide by 2, and we get 3 volts peak. So again, I'm trying to be explicit with my unit, so I include that subscript. That's the value that we are going to use in our time domain expression and in our phasor. So that's kind of what we're after in this case. One done. One piece of information for our time domain. Our time domain expression for that waveform. Okay, next we want to find the frequency. And we're going to do this in a very particular order. We just don't want to find the frequency, we want to find the angular frequency. Okay, we can measure things easily, or there are 3 values related to frequency that we can use to describe how quickly this waveform is repeating itself. The first one is the one that's easy to measure. We can measure the period off of this waveform because we can look at the different times on the waveform. We can't look at how many cycles per second quite as easily. Okay, so we're going to measure period. We're going to convert that to frequency. Frequency is going to be measured in hertz, or cycles per second. And then once we have that, we can easily convert it to angular frequency. Okay, so period isn't really a frequency, but it's closely related to it, and it's the one that we can read easily. What we're interested in is angular frequency. That's the one we're going to use in our time domain expression, our time domain function. Okay, so that's the one we really need, and we're going to work our way through. Okay. So in order to find the period, I need to find 2 points on the waveform that are similar. So that means they have to have the same value. And not only do they have to have the same value, they have to have the same slope as well. So if it's positive going at one point, it needs to be positive going at the other point. So I think the easiest one to pick off here, and certainly the easiest to do math with, is at t equals 0. So read the bottom of the plot. Don't screw up like I did in my outtake video that I just threw out. And we're going to pick that point. Let me pick a good color. No, blue's a bad color. Let's go with this pink here. Okay, so it's a little bit above 2 volts. Now I want to find the next place that that waveform is a little bit above 2 volts, which would be here. But this point doesn't have the same slope, right? This is positive going here. This is negative going. So the waveform isn't repeating itself there. The next place that it's repeating itself is out here. Okay, so it's going to be somewhere in this neighborhood. And it has the same value, and it's positive going. If I take 2 fingers, and you can't see me do this, right, because it's on the screen. If I take 2 fingers and I put them on both points, and then I start to move at the same rate, they should stay equidistant from each other. Okay, it should be a fixed period, and that's how I know that this waveform is periodic. So the period then becomes the distance between those 2 points. Okay, so we're going to look for this, and we call that cap t. So now I just got to read some points off the plot. So if I'm looking at this one, it's a little bit past halfway between by my eye. You tell me what you think, but I'm going to call it 0.33 seconds. Okay, and this one, of course, is 0. We kind of lined it up that way deliberately. Wow! I minimized. You can see my desktop. How did I do that? I tapped with my stylus in the wrong place. Okay. So we got to measure that distance. Let's come down here and find the period. You know what, let's do it in that gaudy pink so it lines up with the color that we marked the graph with. 0.33 seconds minus 0 seconds equals 0.33 seconds. So that's our period. So that's useful, but it's not what we're going to use when we write out this function. So I'm going to take the period and I'm going to find the frequency by inverting it. This is seconds per cycle. We leave off the cycles most of the time. So if we want cycles per second, we just have to invert it. So we get 1 over 0.33 seconds, and I'm going to call that pretty stinking close to 3 cycles per second. And cycles per second has that fancy name hertz after another dead guy. Okay, almost there. That's frequency at least, but it's not the one we're going to write in our expression. We want angular frequency, which is lowercase omega, and one cycle has 2 pi radians. So we're going to multiply by 2 pi. Okay, so 2 pi 3 hertz is going to give us, well, 6 pi radians per second. What does that work out to? 18.85. With a Scotia rounding, of course. Just for good measure, or bad measure, whichever one rounding gets you. Okay, so there we go. We got our frequency. That's our second piece of information that we need. What are we going with on this one? Green? To write out our time domain expression. That's how squished it is horizontally. Amplitude tells us vertical. Frequency tells us horizontal. Phase shift tells us how much it's just translated on the time axis. Okay, so on the horizontal axis, how far are we shifting it? In order to find phase shift, let me get us queued up down here and say phase shift. The most we can do, it's an angle, right? We're going to describe it as an angle. The most we can do is degrees or radians. And honestly, we use these interchangeably as long as we label the unit. So let's see, to find phase shift, we have to say, okay, if this is a cosine, we're going to write it as a cosine. Just by convention, we tend to use cosines. Where would the waveform start if it wasn't shifted? And it would start at the positive peak. So let me pick out a nice color to do this one with. Okay, so we're going to find this positive peak right here. Okay, it looks like it's a little bit before 0.05 seconds. And we want to know how far it's shifted from 0. So this one always starts at 0. The period, as long as you find 2 like points, it doesn't really matter that much. Okay, so let's see. We've got to pick off this time, and we're going to say that's, what do you want to call that, 0.04? I mean, how wrong could I be? 0.04 seconds? You're reading a plot. There's going to be some estimation error. And it's shifted to the right, and that's important. I want you to think back to your pre-calc classes, and when we shift to the right, are we adding or subtracting from our domain variable? This is a time domain, right? So we're shifting to the right by 0.04 seconds. Okay, so how do we do this? We say, let's call it delta t is 0.04 seconds. Now we want that as a degree, so we got to figure out how to take this time shift and turn it into a phase angle shift. And we do that by saying, well, what's a time that we know that corresponds to an angle that we know? Because we can figure out our phase shift theta if we can do all of that stuff, right? We're just doing a unit conversion effectively. So the one that's easiest to find is the period, and we already found that. Look, it's right there. Okay, 0.33 seconds. One full rotation, ready? I'm going to try to do this on camera. One full rotation takes 0.33 seconds. Did my finger get cut off? Okay, 0.33 seconds to go around. 360 degrees to go around, and we're going to use that to our advantage. So this is in seconds. We want to get rid of seconds, and we want to get to degrees. Okay, so I'm going to multiply that by the period, and I'll look at the units later actually. Hold on. I'm going to multiply that by the period, and I'm going to I'm going to divide that by the period, and I'm going to multiply that by 360 degrees. Okay, these are both in seconds, so they cancel out, and I'm left with a phase shift in degrees. So let's see what that works out to for us here. 0.04 seconds times, I'm going old school with the times there, aren't I? There we go. How's that? Just so you're not like, where'd X come from? There's no X. Okay, 360 degrees over 0.33 seconds. What does that work out to be? Okay. 0.04 divided by 0.33 times 360. Okay, and by my math, that works out to be 43.2 degrees. I'm guessing that with my little bit of measurement error there, it's actually closer to 45, but that's okay. We're reading a plot. There's going to be some error. Okay, the only other thing I'm going to say is we moved to the right. We moved to the right, and when we shift a function to the right, we subtract from the domain variable. So our phase shift is actually going to end up having a negative in front of here. So we get negative delta t, and that's going to work its way through. So we got negative 0.04 seconds and negative 43.2 degrees. All right, does that make sense on the phasor diagram? Well, we do have all three of our, let's think about the phasor diagram in a moment. We want to make sure that shift took place in the right direction. We'll do that when we get to our phasor. Okay, but that was our third piece of information. With those three pieces of information, 3 volts peak, 18.85 radians per second, and negative 43.2 degrees, we can write the expression for that voltage. So we can say the voltage as a function of time is 3 volts. We're going with a cosine, 18.85 radians per second, and that's a coefficient of t, right? Because that's where the function is a function of t, minus 43.2 degrees. All right, what was the unit on the magnitude over here? It was in volts peak. We assume peak when we see this form, so we can just say that's in volts. It's not in millivolts, it's not in kilovolts, anything crazy like that. Okay, so hopefully we did that right. I'm pretty confident I did. But we should make sure that we got the phase shift in the right way. But that was our first answer. In order to check the phase shift, we want to take this and we want to perform what's called the phasor transform, or the phasor transformation to this. So we want to get a phasor, okay, using the phasor transformation, or the phasor transform. Okay, now this is lowercase v because it's time variant. When we move to the phasor domain, it's going to be capital V because it's going to be a fixed complex number. In order to perform the phasor transform, we move the 3 down and we move the angle down, negative 43.2 degrees, and that's in volts, right? Because the unit stays with the magnitude. The frequency disappeared. It does that. Okay, we can only work problems at a single frequency. So if I was working a problem with this particular signal, I would keep track of that, but it's not part of my voltage. Okay. All right. Think about this on the phasor diagram. Right. On a phasor diagram, we just take our complex plane that looks like this, with a real component and an imaginary component, and we draw this. So negative 43 degrees is going to be down here somewhere. Okay, and this has a length of 3. Negative 43.2 degrees. Okay, what we're interested in is what's happened. Well, what this depicts is a snapshot at t equals 0 seconds. And what we can see on the plot easily is this distance. So to my eye, it looks like it's going to be positive. Okay, so this is going to be, that distance is going to be v at t equals 0. It's going to be positive, and it's going to be a little bit less than 3. And if we go check the plot again, we should see that at t equals 0. Okay, so if we slide up here, here's 0. It's positive, and it's a little less than 3. It actually looks like it's close to 2. So I feel like we got that shift correct. If we got the shift wrong, I would have drawn it the opposite way. I'm going to erase this because it's going to be wrong. Okay, it would have been up here. Oh, well, wait, we got to think about something else, right? We would have wrongly said that's positive 43.2 degrees, and this is 3. We might have said, hey, it's positive, and it's a little less than 3. Well, that would have also been true. So which one of these is right? Well, they're going to spin counterclockwise. So if this spins counterclockwise, the first thing it's going to head towards is 0. It's not going to head towards its positive peak value. If this one is correct, the first thing it's going to head towards is its positive peak value. Okay, so which one is it doing? So we got to think about those two things, not just the value, but what direction it's going. So here it looks like it's a little less than 3, it's positive, and it's headed towards its peak value. So that lines up with this phasor diagram because it's going to spin counterclockwise. So we did it correct. It's almost like I've been doing this for a few years, and I knew how it was going to work out, huh? Okay, so I'm hoping this is tying together what you would measure on an oscilloscope when you plop down your probe, how you write it as a time domain function, and then how you would write it as a phasor. Okay, this is the other one that's a good result. They're all related to each other. One of them we can measure, one of them we can perform analysis with. One of them is kind of an intermediate form that's important some of the time. All right, next video, we're going to do this backwards. We're going to start with the phasor, and we're going to work to the time domain plot, and we'll go from there. Oh, you want to cheat? Since I created this script with MATLAB with all random numbers, let's check it out here. This is what the script spit out as an answer. I didn't look at this beforehand, I promise. 3 volts peak, 18.85 radians per second. We got that one. 3 hertz. We got that one. 0.33 seconds for the period. And then our theta was -45. So I was right that I had done some rounding in the script. And the corresponding angle would be 315. Okay. Look at us go. We're so good at this. You're going to get good at it too. Next video, let's do it backwards. Stay tuned. Good luck.